Yeah. Okay. Good afternoon and welcome to this first post-lunch session. So the first talk in this session will be given by Meng on dynamical signatures and new paradigms of quantum matter.
Okay. So thanks, Chairman. Let me also start with thanking the organizers to put up this nice program. In particular, I would like to thank Subhro for insisting me to come over to India. And actually, this is my first time coming to India. So far, so good. Back then, Subhro, me, SungBin, and also Chen, we were together in the University of Toronto as a postdoc. We had some overlap together. So at that time, I was a very naive numerical person. I still is, but I'm still is. But at that time, I'm living in my utopian of just studying the model level system and asking the transitions. But after that, I joined Institute of Physics, Chinese Academy of Sciences in Beijing, which is actually a very big institute full of experimentalists. So my several years there, my experimental colleagues try to bombard me with all the discoveries in the new magnets, and actually I learn from them, and I see the needs of that. Some of our simulation can help, at least help partially to understand the result, what they have get. So this is actually what I'm going to talk about. So dynamical signatures in this case is mainly about spectrum in the spin system. And this so-called new paradigm of quantum matter in this context, in this talk, was mainly about deconfined quantum critical point and also spin liquids. Right, so let me, I'm Meng from IOP in Beijing. So let me start with, okay, good. Cannot be very far away. So let me start with some basic facts that my experimental colleagues has been bombarding me with. So this is a compound that has actually synthesized in IOP in Beijing last year. So this is a sister system of herbicide. This is zinc-doped bolowite. This is copper 4 OH6 FBr is a natural mineral. It's called the bolowite. So the bolowite was all these blue dots are the coppers. And for the copper 4 version, this is also copper, but we use zinc to replace it such that this Kagome layer of one and the other are separated. This is the Kagome, the material. And our NMR colleagues at IOP actually performed the NMR measurement of this material. So this is a net shift. The net shift shows that this material at low temperature and shows this spin gapped property. So by the way, first of all, this material is not magnetic. So, and it shows a gap. And this gap actually is a function of magnetic field. This gap becomes smaller and smaller. And if you trace how the magnetic field dependence of this gap, you will see that the slope of the way this gap closes, the slope of this curve actually tells you the elementary quantum number of the spin excitation in a system. In this case, it's spin 1/2. So basically, what that tells you is that this is a system which has a spin gap, which is not magnetic ordered, and the elementary excitation is spin 1/2, which is spin noise. So this is the NMR, and then afterwards, our colleague Li Shiliang at IOP performed the neutron scattering. Actually, I went with him to Germany to do the experiment, and it was very fun. So this is SQ omega as a function of energy for the particular key point. And again, you see that at the low temperature, which is 2 Kelvin, there's a gapped behavior. You can fit a gap here, and as you rise up the temperature, the gap will close, right? And this is the momentum dependence of the system. So this is the powdered sample. So this is average Q. This is average Q, but you see at low energy there's no signal. At high energy, you have to continue. And notice that actually the gap we read from here is almost twice of the gap we read from here. So that means that so the NMR tells the spin 1/2 excitations, but the neutron measures spin 1. The spin 1 is a convolution of 2 spin nodes. So that's actually why you have twice of the gap. So this is the material, right? So the real material whose dynamical signature shows some maybe a topological order. Right. Not only this, actually now we realize that one can dope this system gradually. Consider the composition of the zinc. Also for this material or for another system material. So now combine this two with Hermite space height. There are 3 families of Kagome antiferromagnet magnets that you can play with it, and you can drive the transition from magnetic order, which is for the mother compound, to the spin liquid. So these are actually ongoing efforts. So not only us, but people some other places in the world, in Hopkins, in Germany, and also in Stanford, are following up doing this experiment on this material. This is experiment. So this is for quantum spin liquid, but even for some simple things like this is, I think Li Yuan mentioned this morning, even for the simple material which is believed to realize a perfect square lattice antiferromagnetic system, that there's still some peculiar features of this neutron scattering data, in the sense that at low energy everything is fine. You have spin waves, linear spin waves. You have this Goldstone mode. But at high energy, there's some vanishing of the weight, right? There's some vanishing of the weight. So this is all the spin material, and also if we talk about the dynamics or the transport measurements, or even for the fermion system, it's even more complicated. For example, in this iron-based superconductivity, that above the quantum critical doom, you have some peculiar transport anomaly that need to be explained. Also for the cuprate, right? I think, but this is not for this material and for this talk. It's just to say that there's a real experiment signature that actually calling for the understanding from the numerical, from the theory and also numerical perspective. So with this understanding, so that's actually why now I learned that when I do numerics, I have to keep things in mind. I have to keep this method in mind, that I have to perform numerics that try to bridge experiment, the theory, and also our numerical result, right? So in this context, I will talk about several things. First, I will try to talk about these spin waves for the square lattice antiferromagnet materials that we actually perform Monte Carlo simulation on this, and try to explain how much is the vanishing of the weight at high energy. And this actually nicely connect to the next story, that antiferromagnetic Heisenberg model can be tuned by adding another term in the Hamiltonian to the so-called deconfined quantum critical point. And at that point, we can perform dynamical calculations and to see the spectrum of the real deconfined spinons. And this actually links us to another connection, that this is the spinon at that point is nothing but matter field coupled to gauge field. And from that, our numerical data also reveal this information. This is the main part. If I have time, I will talk about some other work on the model study of two-dimensional Kagome quantum spin liquid, which has a D2 topological order. So we calculate the spectrum and how it looks like. And also for the 3D paracolor quantum spin ice, we also calculate the spectrum, and we can see the gauge photon out of this, if time allows. So yeah, this is the outline. And so these dynamic signatures, I mean, this is hard to get because, as you know very well, that in the quantum Monte Carlo simulations, everything is lived in a so-called imaginary time or multibara frequency. So we do not have the real frequency informations. And to have the real frequency information, people do analytic continuations. But analytic continuation has many versions, and it is well known that it's actually it's a very difficult problem. So it is a difficult problem for the following reason. So in Monte Carlo simulations, what we can calculate is a dynamical correlation function in the imaginary time. For example, these spin-spin correlation functions. And what we would like to have is a spectral function which is a function of frequency and the real momentum and the real frequency. And these two are connected by this so-called kernel. This kernel contains these exponential factors. So from this, you immediately see that at long imaginary time, at large frequency, because of this suppression of the exponential factors, you can have many possible spectrums that give you the same Monte Carlo imaginary time correlation functions. That's actually why the problem is so hard. So going from the spectrum to this is hard. It's actually easy, but knowing this to resolve this is hard. It's exponentially hard, right? This is very hard problems, and people know this. And we Monte Carlo people, recently we come up with this idea. I mean, actually, it's not recent. It's been a while. And it's mainly driven by my friend Hui Shao at Beijing Normal University and my colleague at IOB under Sandwick, that they propose the so-called stochastic analytic continuations. So basically, we Monte Carlo people like Monte Carlo so much that we turn analytic continuation into a Monte Carlo business. So let me tell you how it works. So it's actually very simple. We do not know how it looks like. We want to know how it looks like. So let's just put the most naive ansatz. In that case, it's just a sum of data functions, many data functions. And the position and the height of data functions are the parameters that we need to optimize, for example. So we do this. We can have many data functions. And what we do is just plug this in here and get a value of the correlation functions that you get from Monte Carlo, that you can compare with the Monte Carlo result. So you get these ansatz, you plug in here, you get your Green's function or correlation functions. And of course, a naive ansatz here, for example, like this, all the same height of the data functions, will not be a good guess, right? It will give you a not so good correlation functions. But you can actually quantify how good your ansatz is by measuring the difference of your output compares with the Monte Carlo mean value of the correlation functions. And by doing this, you also respect the error bar of the stochastic measurement of the Monte Carlo itself. Actually, this is very crucial. And because from this, you can actually define the goodness of the fit of your ansatz, which is this chi-square. So chi-square for us is like an energy difference. It tells you how good your ansatz is between, for example, a configuration from this set of parameter to a configuration of another set of parameter. So you get this chi-square, you just write this in the form of a Boltzmann factor. So this now is really like a configurational weight of this particular ansatz. And if the weight is high, that means your configuration is good. If weight is low, that means your configuration is bad. And once you have the weight, you can perform the update. And the so-called update here is just to shift the position of these data functions or massage the height of these data functions. And each update has its corresponding weight. And from this, you can do the sampling of this process. And in the end, what you get is not only just one spectral function. What you get is an ensemble of the spectral functions, and you perform the ensemble average of them. From that, you can get a good quality data afterwards. So for example, you start from this, eventually get something like this. Right? So this is the stochastic version of this analytic continuations. So from this, let's look at what we can get from the simulations. So this is our technique, and this is what we want to talk about from the result. So we start from something, so this is involves several papers. So in this line of story, so we first had a paper that we calculated just square lattice Heisenberg model. We get we try to explain the high energy part. We think this has something to do with nearly deconfined spinons. I will explain. And there are many people involved, Anders, myself, and Stefano, and also I think the main driver is Hui Shao. At that time, she was a postdoc at the CSRC, and now she's a junior faculty at Beijing Normal University. And my student Yan Qiqin was also involved. And from there on, we continue. Actually, we found another model that linked this Heisenberg model to a deconfined quantum critical point. And not only that, we found that there's a duality relation between this deconfined quantum critical point of the spin models to some topological, bosonic topological transition. That was about this duality transition. And here also Yan Qi and Yuan Yaohe was also back then the students at Beijing Renmin University. Right now, he's a postdoc at Flatiron Institute. And from this on, and we know we have a model which really deconfined quantum critical point. We continue, we go to calculate the spin spectrum in the deconfined quantum critical point, and this actually review the spinon features. And this is mainly performed by my postdoc Yusen Ma, now at IOP, and also Yizhuang Yu. Right now, I think he's at UC Davis. Now was heavily involved in terms of understand the data from the gauge field perspective. So let's start. Actually it's we start very simple. We just start with from the Heisenberg model, square lattice Heisenberg model. Everybody know the ground state is nil order. So this is the experiment data, right? Spin wave down here at pi, and at high energy there's something vanishing. So we perform our simulation on this system, on this model, on this simple model, and this is our spectrum, what we get. This is the overall overview. So you see similar things that at the low energy, you have these linear spin waves, and that you also have this enhancement of the weight towards pi. And here you see a black line here. It's just because the data function here is so high that you can't see. But then at high energy, at pi 0, you see some blurring here. So there's some vanishing of the weight, right? So you can already see some overall perspective. And if you do some line cut, if you really compare the Monte Carlo data with the experimental result, this is what you'll see. So for example, let's start from pi half. So this is at this point, for example, at this point. So the squares are the experimental data. The lines are our Monte Carlo result from a finite system size 48 by 48 square lattice. So they match very well, first of all. And secondly, that at this energy, you have a very high maximum peak, right? And above the maximum peak, there's very few weight, almost no weight here. But things are very different at pi 0. If you go to pi 0, which is down here or down here, What you see is that, of course, you still have this maximum peak, which has some weight, but above the maximum peak, both Monte Carlo and the experiment tells you that there's non-vanishing weight. There's a weight there. The maximum becomes weaker at pi 0. And let's look at the things more carefully. So this is actually the position of the maximum peak if you just draw them. So again, so the red dots are Monte Carlo data from a 48 by 48 square lattice, and these squares are the experiment data. So again, so it's meshed very well. So by the way, the linear spin wave cannot explain here, right? Cannot explain this deep of these dispersions. So you have to have some high energy process, other process to explain this. But so the Monte Carlo and the experiment mesh very well. But if you again do the line cut, and now this is the line cut at 0 temperature. I mean, very, very, very low temperature, for example. So for example, if you look at this point, so this is pi, so this k is 1 over L, so it's very small, 1 over 48, so it's close to pi. And this is a spectrum at low temperature, which contains a very high data functions. So it's actually very high, I cut it here, but it's actually very high, and with some tail. And the data function is so high that the weight under this data function is 90% of the area underneath this whole curve. So the data function itself contains 90% of the weight. So you have a very defined, very sharp maximum close to pi, which is it's supposed to be, right? As you gradually move towards pi 0, so things still the same, that you have a high energy. So you have this gap, above the gap, you have these data functions. In this case, for example, close to pi half, this data function now is only 70% of the weight, total weight. So the high energy part is 30%. And the most drastic point is here. Close to pi 0, now the data function is only 40%. So the 60% of the weight goes to the high energy. This part contains 60% of the weight, right? So the message is that here you still have the exact solution. Simulation tells you that here you still have magnons. But on top of magnon, you have something more, right? You have something more at high energy. And this is the same plot that if I just plot the height of the data function from our spectrum along the k point. So again, at pi, you have 90%, it's almost 1. And the minimal is at pi 0, right? So this is the Heisenberg model. This is the property of Heisenberg model. This is another way of writing the Heisenberg model. And from here on, we realize we can actually even amplify this process. So we can simulate the Heisenberg model, but we can add another term to the Hamiltonian such that new physics will happen. And this term is so-called the Q term. So this is the JQ model, this is the Q term, which is nothing but a 4-spin interaction. So this is 2 spin Si dot Sj times another 2 spin on a plaquette or square lattice. This term actually respects the rotational symmetry of the lattice. This term does not break any symmetries, but the ratio of the Q over J will drive the transition from an antiferromagnetic order when the J is dominant to actually a valence bound solid order when the Q is dominant. So there's a transition. So we can simulate this, and actually for the talk right now, so this curve is actually important. So what this curve tells you is again the spectrum weight of the lowest energy at pi 0 as a function of Q over J. And remember I said at Heisenberg limit that when Q equals 0, you only have J, you have 40% of the weight. You still have 40%. But as long as you have a Q, it drops very fast. It's vanishing very fast. The true transition actually happens somewhere around 20. So the valence bound solid is above 20. So even here you are still in the null phase, but your weight of that magnon vanishes very fast, right? So this you can see from here. So then from here, let's go to the JQ model. Let's see what really happened along this line. And JQ model is all connected to this deconfined quantum critical point. I think this everybody knows. And the deconfined quantum critical point has a model realization, which is the JQ model come up with Anders. This is what I just explained. So you have this J term, a Heisenberg term, and the Q term, which is both this vertical and also, horizontal and also vertical. I didn't draw the vertical, but there's another term which is vertical, so that respects lattice symmetry. So this model by itself is actually very complicated. I mean, just the transition itself, right now people still arguing whether there's a first order transition or continuous transition. Even the finite size scaling at the critical point is so difficult, such that it takes us, I think this is a science paper, just to talk about the finite size scaling at the quantum critical point. So this is Wenan's paper. So it's a 2-line scale. So far, there's still a lot of discussion of these models. Our approach is that let's ask a relatively simple question. So how the spectrum looks like. Let's ask the qualitative question. So then this is how the spectrum looks like. So for that purpose, we started this transition from antiferromagnetic phase to the valence bound solid phase. So here I massage the model a little bit such that my antiferromagnetic part or my J part is not SU2 symmetry, but actually it's a U1 symmetry. So I purposely add an isotropy to the Hamiltonian. There's a reason I will explain. But it's still square lattice, and at zero temperature, you still have this antiferromagnetic XY long-range order. And when the Q is very large, you have this valence bound solid, right? So you still have this transition. So then the question is how the spectrum looks like as you drive the system from this antiferromagnetic long-range order and go to the quantum critical point and above the quantum critical point. So this is how it looks like. So what I'm plotting here in this row is the SX channel, the easy plane channel of the spectrum. So this Q is the control parameter. Q point equals 0.2 just means that I'm deep inside this phase, nothing more than this. Just I'm deep in this phase. And this is the SX channel, so this is the easy plane. So I still have my spin wave down here, just like in the Heisenberg model. So this is actually pi, so you have this spin wave. And at pi 0, you still have this small banding and as a continuum above this, right? And the reason of adding an isotropy is that actually I purposely want to gap out SZ. Because I add an isotropy, so my SZ channel, the spectrum in SZ channel is not gapless here, it's gapped, right? The SD is gapless at 0, 0 because this model can map to the hardcore boson and there's some density fluctuation at 0. So this is well understand. This is well understood. Where everything is clear. So then, as I said, on this way, right? On this way, this weight at pi 0 will come down very fast, and this is what you see. So this is actually at control parameter 0.6. So it's close to this transition point, not exactly, but very close. So you see that at pi 0, right, this dispersion really coming down. This is actually pi 0. This is pi 0. This is pi 0. So the dispersion really coming down. And not only is coming down, above it is all continuum. And not only the continuum up here, above pi, you also see the continuum. And not only above pi, you also see the continuum. You see the same thing in the SZ channel. So this is actually something very, very, very neat because I have an isotropy in the Hamiltonian. My spin wave is gapped out here in the ordered phase. But at the critical point, right now the true degree of freedom of the system is no longer your magnum, but the fractionalized spinons. So the S operator can be written into the spinon operator. So the point is not only which S operator is gapped or not. The point is whether the spinon is gapped or not. And the spinon is not gapped. It's gapless at the Deconfined quantum critical point because they form Dirac cone. Because they form Dirac cone, it doesn't matter which channel you look at. What you are seeing is nothing but a convolution of the spinon Green's functions. So if the spinon is gapless, it doesn't matter which channel you look at, they all gapless. So this is a very unique feature that at the Deconfined quantum critical point, you see the signature of spinons. And above the Deconfined quantum critical point, you go to VBS phase, then everything is gapped out because this is the VBS is rigid. You have to pay some energy to gap it out. But actually, there's still something peculiar here. I mean, you see this is a huge continuum above it. So this spectrum is very different from, say, a trivial, very rigid VBS that you have a triplon, for example. The triplon is not like this, right? So this is the whole process. And to make the contrast more clear, we actually simulate another model which realizes a typical, like Landau-Ginzburg type of this magnetic transition. So we simulate another model which again starts from antiferromagnetic phase, but will not end up to some VBS, but to some trivial paramagnetic phase, which has this columnar structure, because in this model we are studying here, this is just all the blue bond, for example, has a J2, and all the black bond has a J1. So what we are doing is just tuning the ratio of J2 over J1. When the J2 is very strong, of course, you have this singlet. But this already does not break any symmetry because the symmetry has been broken already. So you have a transition from here, and this transition is a 3D XY transition. So here, then you see the process. Contrast this with the previous slides. So in the antiferromagnetic ordered phase, you still have the spin wave here, everything is the same. In the Z channel is gapped, everything is the same. You drive the system to the quantum critical point here. This is a 3D O2 transition. You have some critical fluctuation up here, but there's no continuum. There's also no coming down of pi 0. And because you have anisotropy in the model, the SE channel is still gapped. Right? So these two plots is very different from these two plots. Right? So the deconfined quantum critical point is different from a conventional quantum critical point. And above the transition, you go to this paramagnetic phase, you will have a triple excitations. Triple is well defined, it's very sharp. Right? So this is what you will see. So there's a very big difference. And actually, that difference can be looked at even more clearly, more clearly analysis. So this again is the spectrum at the deconfined quantum critical point. Okay, as I said, at the deconfined quantum critical point, you have deconfined spin-on pi flux on the square lattice. But this spectrum is actually more than a simple free pi flux fermion, for example, on a square lattice. Because if you have a pi flux fermion on a square lattice, you have the dispersions. You can calculate the spin spectrum by hand. And what you see is that, again, you have pi 0 and pi and also 0, 0. You have gapless excitations. So the overall shape of this, of course, is very similar with this. But there's a very subtle difference. The difference is that for the free, let's say, fermion, for the free spinon, if you like, as you go down in energy, the weight becomes smaller and smaller, both at pi 0 and also pi. And this is the real system. As you go down in energy, the weight was not changed very much. In particular, at pi 0, at pi, if you go down in energy, the weight actually become higher. Right? So that means the system is not only a free spinon, there's something more. And what is more is the gauge field, is emergent gauge field. So there are gauge field coupled to the spinons. And this gauge field gives this spectrum weight. And both in the SS channel and also SZ channel. And our friend Yizhuang actually performed some RPA calculation on top of these free spinons, put some interaction, take care partially the gauge fluctuations, and they can show that there's some difference, there's some enlightening here, different from these free spinons, right? So actually, how much time I still have? It's not 10 minutes. Okay, very good. So, okay, very good, yeah. So you see, so this is already tells you that you drive your system to the deconfined quantum critical point. You have this emergent spinons. On top of this emergent spinons fill the emergent gauge field, right? So this is a realization of that, right? And from here on, we actually realize, so why don't we, or can we, directly simulate this situation? Because the spin model I'm showing you rely on the emergent properties. Right? I start with a spin model. I have emergent spinons. Spinons are not in my Hamiltonian. So I'm asking myself the question, can we study a system which just the starting point is some spinon coupled gauge field? This is actually possible. I mean, we realize this is actually possible. It's actually possible to simulate this. This is a later work from us that you can directly simulate this U1 gauge field coupled to fermion matter. So this is then a simulation we performed not by the spin Monte Carlo, but also by the fermion Monte Carlo. So this is a model. This is a Hamiltonian. Let me just directly go to the next slide. This is easier. So this is the partition function, and this is the action. Maybe this is simpler. So the action has the fermion part, has a gauge field part. So the fermion part, the Lagrangian the fermion part, is a fermion live on the square lattice. That's what I'm saying. The fermion, these dots are the fermion live on the square lattice. While the fermions are hopping, it pick up a phase, right? It pick up a phase. This phase is the phase mod 2 pi. So this is the U1 gauge field, if you like. So the fermion pick up a phase, but if only that is still not the interacting system, because you need a gauge field to fluctuate. And this is the gauge field fluctuations. So the fluctuation is nothing but the difference of the phase for a particular bond over the imaginary time divided by the imaginary time. So basically, it's a time derivative of the gauge field, the square of the time derivative. This gives you the fluctuation of the problem. So this problem is the U1 gauge field coupled to the spin fermion matters. Actually, the other day I was just looking at Xiaogang's book. He actually talked about this in the chapter 6 of his book. At the time he was talking about this, he was mainly talking about the gauge field part. So this is a 2+1. So it's actually a question for people that whether at the 2+1, do you have the deconfinement or not, right? At 3+1, you can show that in the gauge field we will have deconfinement, but at 2+1, the pure gauge field cannot have deconfinement. So the question back then, it's posed in his book, was that if you couple the gauge field to the matter field, can you have the deconfinement or not? And this is a model that realized that situation. Right, so then we studied this model with Monte Carlo, and what we do is just we have, in the presence of this gauge field, we write down the Fermion determinant, and then we can simulate the Fermion determinant, right? This is, and the partition function, and the Fermion determinant, the trace of the Fermion of this Fermion part is a determinant, and we can actually study the even number of the Fermion flavors. We cannot do the odd; we can only do even. So this is what we get as a function of the strength of this gauge field fluctuation. This J was a term here, or the J is a term in the Hamiltonian. So the NF is number of Fermion flavors. The J is the control parameter. The T is set equal to 1. So it's only a J is control parameter. So the J contains the strength of the fluctuations, and this axis is a number of Fermion flavors. And from this, we can see that from the two components of the fermions, you already have this U1 deconfinement phase, and that phase will go through a deconfined to confined transition. In this case, eventually the fermion will be gapped out and form an antiferromagnetic long-range order. And if you increase the fermion flavors, you have more variety coming up. So you have this U1 D phase again in the full component, and the confinement is realized first in the form of a valence bond solid, which is also a gapped phase, and then eventually go to antiferromagnetic phase. And the higher flavors, you only have this valence bond solid. So actually, this particular phase down here was the deconfined quantum critical point, what I was talking about for the spin models. At that point, at that part, it's just a point, and here is a phase. Right? So this is what you can see. And yeah, I think there's a, sure. Yeah, so that is also not clear. So what our data show is looks like a continuous transition. And on top of that, I cannot tell you much. Yeah. So the work done for this part was, this work was mainly about this phase diagram, and we try to understand the property of this U1 deconfined phase. And one particular property I want to tell you, for example, is that, let's just focus on this plot. So this is, again, for the 8-component situation, where we have very large phase of this deconfinement phase space of this deconfined phase. And we are inside this phase. We measure the spin-spin correlation function of the problem, also the dimer-dimer correlation of the problem, construct out of these Fermi operators as a function of distance. So this deconfined phase, fermion form Dirac cone, is gapless, but at the same time, the fermion fills the gauge fluctuation. So it's actually a strongly coupled system. And because the fermion is gapless, in this log-log plot, you're expecting some straight line of the correlation functions, which means that the correlation function is a power law, right, in the real space. But what is unique here is that usually, for example, if you measure spin-spin correlation function, which, for example, read like here, the spin-spin correlation functions, in terms of fermion operators, or in terms of spin operators, one of the spin equals to 2 spin-ons, so the spin-spin equals 4 spin-ons. These are the 4 spin-on correlations. And dimer-dimer, I didn't write it, but actually this is the 8 spin-on correlations, or 8 fermion correlation functions. So for a free system, like a Dirac system, you wouldn't expect they have the same power, right? Because if the Green's function is 1 over r, this will be, the spin-spin will be the 1 over r to the power of 4, the dimer-dimer will be 1 over r to the power of 8. They will have different powers. But because of this phase, it's a strongly coupled system. It's not a free system. That the prediction was that these 2 correlations actually had the same slope. And this is what we see. So this is the uniqueness of this phase. And in fact, this slope actually tells you that this critical phase has a particular anomalous dimension. And this anomalous dimension, this eta actually has some prediction, has some large N calculation as a function of fermion flavors, 1 over fermion flavors. Eventually, it will go to 4. I mean, our data, you see the error bar was embarrassing, but actually it's going to the same trend. The error bar is large is because this is the fermion simulation. The fermions are usually harder than the spin models. And we have to do very hard job just to get a 16 by 16 square lattice. under control. You remember for the deconfined quantum critical point, I can easily go to, for example, 48 by 48. This is very difficult. And now we're actually still improving our algorithms such that we can do even larger system size. So this is this part. Let me just skip this. So let me tell you, this is actually very important. So then how do you, I told you that this phase, right, it's a strongly coupled phase. This phase has some very peculiar signatures. For example, the spin and dynamic has the same power. But not only that. So what I'm plotting you here, this is just very recent data, so this is not very clear, but let me just explain to you. So what I'm plotting here is the sum of the phase of one square lattice plaquette, the phase of the plaquette, as a function of Monte Carlo step. So inside this U1 deconfined phase, that this sum of the phase actually accumulates always to this plus pi or minus pi. So this two distribution means plus pi or minus pi. That means you are really forming the pi flux of the gauge field. The pi flux is very stable in the U1 deconfined phase. As you gradually drive your J, you go through, for example, this deconfined to confined transition. You go to this confined phase, and this pi flux lost the coherence. So this is all over the place. So this is a signature of showing that in the deconfined phase, the gauge field is gapped out, the fermion is gapped out. In the confined phase, the gauge field is gapped out, the fermion is gapped out. This is more or less trivial, and this is not trivial. And this transition is even less trivial, and this is actually what we are working on for that. So, yeah, I guess, 5 minutes? Oh. Okay, so 5 minutes, so this is only the first part, and let me just go to the second part, just very short. Let me talk of this part. So this is about the parallel system, and we can simulate with Monte Carlo as well. Let me skip all this, let me just go to the last part. Yeah, this is it. So, again, Monte Carlo simulation with analytic continuation. That we simulate this on this XZ model on the parallel lattice, three-dimensional parallel lattice. And we can only do the ferromagnetic transverse part because of the same problem, but it still gives the good physics. So we simulate this model, right? And this is for example, for a particular choice of this J perp over JZ. So JZ is actually the largest energy scale because this gives the fluctuation. The J perp gives the quantum fluctuations. For a particular choice of these ratios, you can calculate the specific heat as a function of temperature. And what you see is that as you gradually cooling down the system actually go over the specific heat go over two peaks. The first peak is in the energy scale around 1 or around the value of the JZ, because this is the energy scale that the classical fluctuation the spin start to feel the classical fluctuation. And corresponding to the entropy, this entropy curve, entropy actually go from log 2 to the Pauling's plateau. Right? So this is what you see. But if you keep going down in temperature, the specific heat actually climb up another peak. There's another energy scale below which the entropy is released. And this is the energy scale actually tells that this classical manifold will form a unique state by the quantum fluctuations and enter this quantum spin ice phase, right? And people have been talking about this for a long time. And for example, this is a very typical plot. I mean, people usually do, and this is actually a very nice review by Gingras, that to attack this problem is very complicated. So people have to go through many steps. You go from XXZ, you do some map, you do some system, and from this you can do some calculation of simulations. Our approach is that let's just directly simulate this. That is what I'm showing you. Let's just directly simulate this. And you already see the specific heat. And I think the most interesting property of this system is whether you see the gauge photon or not, below the second peak of the energy scale. Yeah, it's exactly that energy scale, actually. So in our unit, I mean, that's what I'm saying. So this is 1 over 1,000 in the particular choice of this ratio of this. I think the ratio was that this is 0.1 and this is 1. So this first one is, in that setting is 1, the second one is 1 over 1,000. This is just the energy scale. And we have to calculate the spectrum, for example, in this point or in this point. So we calculated that, and you can see. So this is what we get, and this is what you would like to have And this is the ideal case, right? Everybody knows this is the gapless, this is the gauge photons. So of course, the real simulation is difficult. You cannot do really large system size. In fact, this is actually just a 8 by 8 by 8 three-dimensional size simulations. But we can still see some signature. For example, that is this dispersion, if you count this dispersion, is in a very small energy scale, right? This is 1/1000, which is matches. And it's actually going to 0. I mean, you cannot tell whether it's linear or not, but it's actually going to 0. And if you integrate out the weight of each of this color, each of this of the momentum, the overall weight actually also going down. This is overall weight underneath all this spectrum, all the spectrum. And the weight is vanishing, and this is what you would expect. So the simulation actually tells you this, right? Really tells you this. And in the same time, this is just means different direction because the green zone is three-dimensional. You have to choose different directions. In the same time, if you measure, so this is the previous slide was the gauge photon. If you measure the spinons, you see the spinon was actually relatively easy. The spinon is just S plus S minus in this language. That is the dispersion is at a very high energy. The gap is around 1, so it's relatively easy to see. And you have this continuum, right? And in this continuum, the weight is not homogeneous. Actually, the weight was very high in the upper part. And this has been actually discussed by some other analytical or semi-numerical method. Yeah, so you can see this. You can see the spinon, which was not very unexpected, and you can see the gauge photon. Actually, this is, to me, was a bit unexpected because I don't think before we do the simulation that we are able to resolve this energy scale, but with our method, it is actually possible. So with this, let me go to this part and let me stop here and let me just take some questions. Yeah, thank you. Yeah.
Questions?
What fixes the capital N omega, the number of delta functions in your stochastic analytic continuation method?
What do you mean?
In the stochastic analytic continuation method, you have the number of delta functions.
Yes.
What fixes
like
that?
10,000 or even more.
Okay.
Yeah. It's more than the imaginary time you have.